Okay, so instead of sending you memory stick and you have to pass one to the other, you can go just to this website, and there you have the notes of yesterday, and you also have the files that you will be using today. Okay, so I hope you have internet and can download it very quickly. You have internet on the computer? Yes? Okay. Okay, let me put it, I will put it back up. That's my website. You can find all kind of other things there. My other courses that I teach, other recordings. I have a YouTube channel, exercises. So if you feel like you want to get something to do, you can just go and check what the information we have here. Okay, so just type it on your browser, and you should get to my website, and then there are two Excel files that we are going to use today. And you also have the PDF of the notes of yesterday. And I will put there all the PDF for every day. Yes, so we are, today the first focus is going to be to talk about this IPR, TPR equilibrium, downhole. Okay, and if you remember how it should look like or how we expect it should look like, we have PWF versus Q of gas. Okay, we are talking about dry gas, and that rate is at standard conditions. So the IPR should look something like that. Okay, and that equation you already saw it with Professor Ali. That was C of the reservoir called the back pressure equation minus PWF squared to the power of n. Okay. That equation you covered some other place. I gave you yesterday some, refreshment where it came from, but actually, that's what we use. And then we have this equation, and for that we're going to use this tubing equation that we discussed yesterday. Okay, that was, if you remember, P1 equal to P2, or the opposite, I think. Yeah, P1 squared P2 over ES squared minus QG squared over CT squared. Is that correct? I'm not sure if here is, I think it's P2 equal to P1, right? Can you check your notes? Okay, just check. We can go to the notes. Okay, P2 equal to P1 minus Q. Okay. So that's correct. P2 equal P1 minus Q. So let's go and jump right into it and open, please, the file that I gave you. That is called dry gas, single dry gas well flow equilibrium. Okay, single dry gas well flow equilibrium. Okay, so let's see what we have in this sheet, and so we have. Okay, we have first, so we say to create IPR, okay, we need the back pressure coefficient, the exponent, and we need the reservoir pressure. These three things. Okay, so we come here, we have reservoir pressure, correct? We have the back pressure coefficient, and we have the back pressure exponent. That's fine. We have everything we need on the IPR side. And on the tubing side, we need S, the elevation coefficient, and we need C, the constant of the tubing. Okay, so we go back to our input. Remember, it's in red. So we have elevation and the tubing. We have also something else here, flow line, but for now we are going to neglect it. And you see the trick we're going to make. So the system that we're going to analyze is a well, and I usually make it too long. So okay, that is extremely close, let's say 8 meters to the separator, and there is a separator here, and that separator has a pressure of around 40 bar. Okay? And you have a choke that is fully open, so that one doesn't account in our calculations, and you have a well that actually is vertical. Okay, and okay, and we want to make the equilibrium exactly here, PWF. Okay, that PWF is flowing bottom hole pressure, and it's just in front of the perforation. Okay, just in front of the formation. If you are talking about a horizontal well, you're just there in front where all the fluid starts to flow inside the well. Okay? So we're going to make it here. So for that we have to go from reservoir pressure to that point, and then we have to go from separator, that basically this distance is very short. Okay, so we will say basically assumption. An assumption is that PWH is constant and is equal to P separator. Okay, because I have fully open choke and the distance is extremely short. That clear? Yeah. Okay, so I suggest to solve it, I suggest first to make the following below. Let's make a column that will be, this equation gives you the rate, right? It takes as an input the PWF. Or you can have it the opposite also. You can use the rate, and then you can use the rate and it can give you bottom hole pressure. Yes? But, the problem, if we write that equation, so the thing I like to put here an independent variable, okay, and I'm going to choose PWF, okay, in bar. Why do I use pressure instead of rate as the independent variable or the value to calculate my equation? Because pressure, I know the range of flowing bottom hole pressure. Okay, rate, I have no idea how much this well can produce until I make the plot, right? I don't know beforehand. But the pressure I know is bounded between reservoir pressure and zero, just basically atmospheric. If I manage to put there atmospheric pressure or vacuum, then that's the range. It cannot go. So I suggest here using PWF as the independent variable. Okay, and here will be from PR, and then I say let's make intervals of maybe 20 bar. Okay, the reservoir pressure is 300, so let's put here PR minus 20 bar, and then here is the one before minus 20 bar. Okay, so if this is, that will be P2, this is P2 minus 20 bar, P3, and then this is P3 minus 20 bar, and this is P4, and so forth. Okay, just all the way until I reach 0. And then here, now the first point is to calculate IPR. So I'm going to put here at the top something identifying what it is that I'm calculating. And I'm going to calculate, so now I gave the pressure, and I want to calculate the rate of the well in standard cubic meter per day. I also put the units. So here is where I'm going to use this famous equation, CR PR squared minus PWF squared to the power of n. Okay, and I have to use, for these numbers, I have to use, they are up here in my cell, so I have to use this one here, and the back pressure here. Okay, and the bottom hole pressure, I'm going to take the one to the left. Yes. Okay, and so forth, and then I do it for the first, I drag it down and I have the rate, and then I will have the IPR. Okay, now the next step, I will say, okay, so that's the IPR. Let's make another column, and now let's make the TPR. Okay, and I suggest really, the IPR only exists after I make this plot. Okay, I will find something like that. Okay, and the IPR only exists between this range of rate. Okay, so the intersection should be also in that range with the TPR if there is an intersection. Okay, so I suggest just using the same rate range. Okay, don't invent anything new, because I know the intersection has to be between these two, cannot be outside. Okay, so I suggest here TPR. I calculate again flow in bottom hole pressure, but now this time, remember, this one was the available. Okay, and this one is the required, and these two, they have to be the same. Okay, and here I'm going to use, which equation I'm going to use? The tubing equation. Okay, this equation that we mentioned before, P2 squared equal to P1 over e to the s minus Q gas squared over Ct squared. Okay, but what I have to clear from that equation? What do I have to clear? What do I have to solve in that equation? In that equation I have, if I want PWF, is that P1 or P2? PWF. Remember, P1 is always the inlet of the tubing, and P2 is always the outlet of the tubing, of the conduit. Okay? So in that case, I want P1. Okay, so I have to return the equation to clear it so it will be explicit in P1. Okay, and then I apply the equation here for these rates. Okay, so how the equation on P1 looks like. I had it someplace here. Okay, actually here is like a trick. I already, there is some, you already have P, no, that's wellhead pressure, so that's wrong. Okay, that's not the right equation. We should use P inlet, this one here. Okay, because it's the P at the inlet of the tubing, which is the flowing bottom hole pressure. Okay, and again, what that equation requires as an input, okay, requires the rate, which I'm going to take from here, okay, the rate calculated from the IPR. The CT, I take it from here, okay, and the S, the elevation coefficient, is here. I take it from, let me put just a star, I will take it from here. Okay, and then that will give me the flowing bottom hole pressure required, calculated from the wellhead, from the separator side. Remember, we have to, when you'll see in Excel, maybe when you substitute all the values in a function and then you drag it down, if you want some values that they don't change, because it will change, for example, Q for the first one, it will take you from this one, and then from the second, it will take you from the one on the left. But you don't want to do the same with the C and the N and all the constants, so you have to freeze them. Okay, and to freeze them, to freeze the cell in Excel, you have to use to freeze cells in Excel, you have to use F4, okay, once. And that will put a dollar sign in front of the column, okay, and a dollar sign in front of the row, and that means that it's blocked. That cell, no matter if I drag it to the right, to the left, up and down, it's always going to take the same number. Okay, so remember to freeze, that causes many problems, when you're doing the exercise in class. Okay, so let's go, and I suggest you start to do it with what I suggested here. But one more thing, see here the functions that we have. You always, I recommend when you get an Excel sheet, always go to the VBA first to see what it has inside. So you see IPR, and that gives me what it's going to give as output, the rate. Okay, that's not what I need. IPR PWF, that's what I need. Okay, so that is the equation I have to use. And in the case of the tubing, I need P1. There are three equations, one that gives me rate, one that gives me P1, and one that gives me P2. So I have to use the one that gives me the inlet pressure, which is the flowing bottom hole pressure. Okay, so after that, you call the functions, you have to make the table. So I suggest we pause here, and I give you like 10 minutes so you make the plot. Okay, make the two curves, and then tell me what is the intersection. Okay, so we said we create one column called PWF. Okay, bar. We can put bar below. And this one we call PWF available. So we are sure how, actually that we're going just to put, it will be the one from the reservoir, the IPR. Here I told you, we know the range, use reservoir pressure, and then we say we want that cell to be minus 20. So it will be kind of even spaced steps. Okay, bring it down. Wait, that size is fine. You can still read. Yeah. Okay. Yes. So afterwards, I have to calculate the rate. Okay. So I say QB in standard cubic meter per day. Or if you're working with some other units, standard cubic feet per day. And here is what I call my function. The function, I have two ways to call it. I can use the trick that I told you, fx, find in the menu, or I can also put IPR, you see, and now it appeared, the two IPRs that I have. So I'm going to use PWF, no, sorry, rate. And to get which one goes first, then I can press the fx. And here is the C, and what I told you, you select the cell, but then you have to remember to lock it with F4. You see, two dollar signs, they appear before the column and before the number. And also I block it. PR is the first one, and I block it also. PR shouldn't change. And then PWF will take the one from the left. The first cell, by chance, we put it like that, PR, the PWF is equal to PR. So I should have no flow. And then I can just click here and drag it down. Or another trick is I just click here and double click on when I get the cross, okay, when I get the plus. Okay, so we are getting around, sorry, this is still, I haven't reached 0. So 44, let's do it, every maybe 40. I think 20 is too many. Okay, 64, 24, and then I'm going to say 0. Okay, and then I say if I manage some reason, okay, impossible, if I manage to put in the bottom hole the pressure that is vacuum is 0, even below atmospheric, I will get a rate of 3 million standard cubic meter per day from this well. Okay, that is around how many standard cubic feet is that? You have to multiply by 3, is it? Well, that's, will be some homework. Okay, so that's what I call IPR. We're going to plot it. To plot it very quickly. Okay, so I want to add one. I'm going to put IPR. Okay, and that will be for reservoir pressure equal to 304, right? Just to be sure at which reservoir pressure that IPR was calculated. Then X, in the X I always use the rate, and in the Y I use the bottom hole pressure available. Okay, and I can also put a line. I'm not sure why it didn't come with a line. I want to put a line. Okay, and I move it. Remember the convention, we put it in. So here I'm going to say equilibrium at bottom hole. Okay. Those of you got the same? Yes. Do it again here. Pressure. We said we know already the range of bottom hole pressure. Okay, it has to be something between reservoir pressure to almost, I could put 1 bar atmospheric pressure. Then I said, okay, this one will be taken from the input. Okay, that pressure. I freeze it. Okay, I don't want that to change. And then I say I just have to distribute. I have to create points because Excel to plot it needs to have numbers. Okay, it needs to have a collection of points, of values. And I say, okay, I'm going to do it every 40. Okay, you can choose any number you want. You can have 20, but then it will take a long list of numbers. I use 40 to have like 10. Okay, 10 points. I think it's fine. So I say this cell is equal to the previous minus 40. Okay, and so forth. Reach 0. Okay. I want to calculate with the IPR this CNN equation, not the news channel, the equation. I want to calculate from here the rate. Okay, so I have to use exactly that equation. You can type it manually, or you can use VBA, which is much simpler. So you come here, fx, and search for the function, and it's a function that I define. So I go to this user define menu. I go to IPR that gives me the rate, okay, QG, and I select back pressure coefficient. I block it with a 4. Back pressure exponent, I block it. Reservoir pressure, I can take it from up here, okay, reservoir pressure where it is here. I block it also. Then flowing bottom hole pressure, and that will change. When I drag it down, I want to use different bottom hole pressure and tell me what rate I'm going to get from the formation if I apply this pressure, okay, at the bottom of the well. Okay, clear? Yes? Okay, crystal clear. Okay, now we got that plot, okay, exactly how we want it. Something that goes down. Available, always you have to get it into your mind, goes down always. If not, something strange, something wrong. Okay, now we want to make it nicer. So let's put maybe 16, bold. We want to add the titles. So that's gas rate, QG at standard cubic meter per day. And that one is flowing bottom hole pressure, okay, PW, and that will be in bar. And what else do I need here in this plot? Maybe the lines to make them a bit darker. Okay, and maybe this one I can also make it thicker. Yes, and I want to change, I don't like this. It's a very long number, difficult to read. So I know it's in million, so I will use just scientific notation. Okay, so for that I go format axis, and I go to here at the bottom, I think, and then I have an option called number, and then I change it to scientific. Yes? Okay, so far so good? Yes? Okay, now that was the IPR part. Now we go to the TPR. Now we go to the TPR. And in the TPR, I told you that we have to use that equation, okay, with P1, tubing P1. But I'm going to use exactly the same rate because I say, if there is an intersection, it has to be where the IPR exists. It has to be in this range, okay, from here to here. So that's the range I'm going to use. So which equation should I use here? TPR I say PWF, that would be the required pressure, okay, calculated from the wellhead that I have a constant pressure downhole, okay, counter current that has units of bar, okay, and now comes the tricky part. Which equation should I use? Okay, so let's see. No, it has to be an equation called tubing, right? Tubing. But I have three equations that are called tubing: P1, P2, and Q. Which one should I use? P1, okay? Because I want the pressure at the inlet of the tubing, okay? Exactly at the bottom hole. So P1, and that requires the tubing coefficient, CT, that I have it here, okay? I lock it. Remember, when I drag it down, I don't want any mess. And the elevation coefficient, then the pressure at the wellhead, we say is extremely close to the separator and the choke is fully open. Okay, so I'm going to assume that the wellhead pressure is the separator pressure, 40 bar. That one I also block. And last, I have to use the rate, okay, of gas. So here you see I got a number. I have a static column of gas and I still have a difference. Okay, here is 40 bar and here is 43. Why do I have this difference? Okay, you see here the number that I'm getting, 43 bar, when there is no flow. I have 40 here at the top of the wellhead and 43. It's just the hydrostatic, okay, column of the gas, just by hydrostatic pressure. One, you will see now this is a well of 3,000 meters, like yeah, 10,000 feet more or less, and it gives you a pressure. If there is no flow, there is a pressure difference of 3 bar between wellhead and bottom. Yes?
How can I block? I don't know.
With F4, you press F4. You see in the upper part of your keyboard, you have all of these
F4.
Yeah, F4. Or you can also put the dollar manually yourself. You can put dollar before the E, the column, and the dollar before the row. Okay? Okay, then I got these numbers. Okay? And you see, initially I don't get, I'm getting the trend that I wanted, okay, or the trend that I expected. That at low rates, the pressure is very low, but when I start increasing the rate, then I need more and more pressure at the inlet of the tubing to produce that rate, okay, against 40 bar. That clear? Yes? Okay, so now let's plot it in the same plot here. I'm going to say at and TPR for PWH equal to 40 bar, okay, and the x-axis is the rate and the y-axis is the pressure, okay, the required pressure. And you see I got exactly, there is an intersection, there is an equilibrium point between the two, okay, as expected. Any of you got this graph, or you prefer to do it later at home with the video, or yeah? Or you want to spend more time and I give you time and then you work on it for in class? Huh? Hmm? How to handle? How do you mean to handle?
How to sketch?
How to sketch? Okay. With you have to go here, insert. When you are in the data, you have to click insert and you have to select at the top. Okay, the plot. Okay.
No, for the ticket. In the same
Oh, you have to right click, say select data. Okay, and there you add another series. Okay, and there you have to select again X and Y. Yes. Yeah. So what do you prefer? You want to spend, because I can give you 20 minutes more and you work on it and you try to do it yourself. I think we can do that, right? If you want. At least you do one, and then the other ones I will do it, but you know already what I'm doing. So let's. That's what I got. So now I show you how it is done, and you have to make it yourselves. Okay. Okay. So we say, from what I got, I hope you also got something similar. We say they have the shape that I expected. Okay, which is a very quick QC that you can make, quality control, and that seems to indicate the intersection is here. It's around maybe 2.8, between 2.5 and 3. Okay, 2.8, 2.7. But I want to know, what if I want to know exactly the value? Okay, so what I suggest is, you want to have the available minus the required, okay? And they should be, for all of this range, this curve minus this one is positive, right? We're starting getting small, small, smaller, 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 until here there is a change. And now the required is more than the available, and it becomes negative, okay? So there is a change of sign. So I suggest you create another column here, and I say PWF available minus PWF required, okay? And you say this one minus 43.2, okay? And you continue, extend it, drag it down. And you will see where the intersection is in this point. Let's do it very quickly. So, but what's the logic behind that? Because I have two functions. It's like I have here one function called f1 that depends on x, okay? That depends basically on the rate, qg. And I have another function that is called f2 that also depends on the rate, okay? And I want to find a qg, a qg star, okay, or a qg equilibrium that makes the function f1 of qg exactly equal at the function f2 of qg star. Okay, exactly equal. Yes, and you have the equations, and basically you can do it mathematically if you like. But when the system becomes, we're using more complex equations, we're using simulator, so it's not so simple to do it analytically. Okay, these equations are simple enough that you can do it analytically, but usually it's not that simple. So the approach that we made, we have methods. Maybe you had some courses in numerical method that they have a function fx, okay, and the function does something like that. Here is 0, okay, and it has an intersection fx star equals 0, right? How did you call this method? It's called root finding, okay? Raíz, para conseguir la raíz, ¿no? Do you see this method in, you had some numerical in math, okay? So there we have a bunch of methods, okay, that are, for example, Newton-Raphson. Yes? The Newton-Raphson, what it did, I started with the seed called x0, right? And then I say I have the derivative at that point, then I shoot, okay? I find another x0, I have the derivative at that point, then I shoot, I have another x, then I find the derivative and I shoot, and I start to converge towards the fx equals 0, right? You saw these methods. There is also another method called bisection, in which you have to have two values and then you start closing in to the number, right? That number, you had it also. Remember, if you remember bisection I have 2xa and xb, okay, and they have to be all the time of different sign, okay? So I say I make the average, and the average, let's say someplace here, okay, I made it too close, but okay, I make the average of xa, let's say it falls here, plus xb divided by 2. Okay, and then I evaluate. If it has the same sign as xa, then that will be my new xa, and I leave this as xb. And then again, I make an average. For example, the average is here. And if he has the same sign as xb, that will be my new xb. I again do an average between these two. I have this number, and I make again an average, and so forth. Okay? All the time have to have two values that give me different negative and positive value of the function, and I average, 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 and I go and close to the solution. Okay? That's called bisection. But the point is that we have these methods that they work when I want to find equal to 0, but not when I want to find one function equal to the other. Okay? But I can make a trick. Okay? I can make a third function, f3, that depends on the rate, that is equal to f1 of q minus f2 of q. Right? And there, that function is the one I want to make equal to 0. And then I can use any method that you learned before. Any of these, they are called root finding method. Yes? Okay? So I suggest to create exactly that function, the difference between the available and the required. Okay? And then see where it changes sign. And then we will try to use, we don't have to program. You think about Newton-Raphson and you say, oh, that's very complicated. That gave me nightmares in the exam. I don't want to go back to it. But no problem. Excel has already something pre-programmed that can help you to find exactly the solution. Okay, when that's 0. We are going to see that just right away. Okay, so let's create another column in your Excel sheet that will be PWF available minus PWF required. I say this is equal to this available minus this required. Okay. I drag it down. It should be, if I did it properly, positive, 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 and there is a change of sign. That means that the solution is someplace between 2.7 million and 2.9 million standard cubic meter per day, right? Now, how do I find exactly? I have to use this Newton-Raphson technique, okay, to drive this function to 0. So for that, okay, for that, and the only variable that we use as an input is this one, okay? This is the one that we typed manually, but this was a function, this was also a function, and this is also something that combines these two functions, okay? But the only one that I'm changing, my input variable, is the PWF, okay? So basically I have to change this one to drive this one to 0, yes? So let's do it manually. We can say, okay, 54, it was not 54, maybe 50. No, made it more negative. So it has to be something more than 64, maybe 69. It's getting closer to 0. Now I use, for example, 73, okay, 79, okay, 82, getting close, 84. Humans, I'm very close now. I think the rate is 2.8. For practical purposes, you might say that's the equilibrium rate, okay? But I had to do many iterations manually by myself, okay? And that's not good. I want someone else to do that work for me. You can take your little brother or sister, okay, try different numbers until you find the solution. But let's find a more elegant way to do it, okay? So what I suggest is you go to File, and you go to Options, okay? And then you go in the menu on the left, you go to Add-ins. Okay, you click there, and then you see here a button called Go. You click there. Yes. And then you have to tick on the one that says solver add in. And this solver is like your little brother, but very powerful in the computer that is going to find the solutions that you want, the solutions for you. Okay? You click here. In my case, I have already activated, but in your case, maybe not. Who has used solver before here? Nobody? Okay. You click OK. Yeah. And now what happens is that if you go to the data tab here at the top, you will see solver to the right. This one should appear. Okay, all of you got it? Yes? Okay, so let me show you how it works. But let me first just copy that just in case someone wants to. Okay. The other ones don't care too much. I just care about the solver at this point. To say activate the solver. Okay, and I'm going to show you how it works. So let's say, okay, you open it, and first over, the first thing it asks is for an objective. How is it in Portuguese? Is objetivo. Does it say objetivo in the? I say also is it solver or what is the name in Portuguese? Solver. Huh? It says the same, solver. Okay, because in Norwegian it's problem löser, which is problem solver. Okay, maybe you got something different. Okay, so say what is my target? What do I want to to what do I want to achieve? So say my objective is this function f3 that I created. Okay, and I'm going to take this number here, for example. I want to drive it to a value of 0 exactly. Okay, and then I have to say, okay, how I want to do that, what I'm going to change in order to make that value go to 0. And then what I want is to change this PWF, okay, exactly that one. Okay, nothing else. What I want, the value I want, can be minimum, maximum, can have a specific value, and then what I have to change, that to get that number. Then I click solve, okay, and then I found exactly 84.3783, etc. Okay, just try it. Try it on your computer. Okay, so that's the solution 84, and the well is producing 2,850 standard cubic meter per day. Okay, now I want to talk after we have this exercise. Okay, we have done this calculation. I want to see. what affects that intersection. Okay, what affects, and so the first thing I say, it's what happens if reservoir pressure goes down. Let's say we're not looking at the well now, but we are looking at it in 2 years, where the pressure dropped, let's say from 304 it dropped to 250. Okay, how that's going to affect the equilibrium point. Okay, you can do very easy the calculation, but before that, let's try to sketch it to see how it looks like, and then we do it very quickly. It's going to be, if you did your Excel sheet correctly, it should be very extremely fast to see how that will change. If reservoir pressure, we said reservoir pressure is this point here, right? Okay, now it's 304. Now let's say it dropped to 250. Now that's the new reservoir pressure. How the curve looks like. I think you talked a bit about it with Professor Ali before, right? So how the IPR will change? Well, actually it has the C and the N, they are the same. They don't change with depletion, okay? So actually we'll keep the same shape. So that discussion we call effect of depletion. Okay, that means PR is reduced on the equilibrium rate. Okay, and if it goes down, we should expect something like this. And let's use another color, right? Yes or no? That's what you expect, is scale down just because the pressure changed. Okay, the shape usually shouldn't change much. So now I have a new rate, and actually it's lower as expected. With depletion, the well will produce less and less and less. That clear? Okay, so that's what we expect. So we go just to verify it, we go very quickly to our Excel sheet and change reservoir pressure from 304 to 250. Okay, I change automatically. Okay, and now the intersection is not at 2.8 but at 2 million. As simple as that. Okay, and you can assess very quickly what happens with depletion. Okay. um, Yes, well, I could put another IPR, okay, just to plot it so you have it. So where do we put it if we do that? I suggest picking here, that's IPR for PR equal to 304. And then I'm going to make one more exactly the same like that, and I'm going to put it here, and I say IPR for PR equal to 250. So this pressure will be 250. You already know, I guess you already covered material balance, right? How do you calculate the pressure after we take material out of the tank? Did you cover that? Dry gas material balance? Not yet? Okay, so you will do it very soon, I guess. Okay, minus 40. Then I drag down all the way, let's say, to 0. And here I have to use the same IPR. Okay, so I can copy and paste. Now the reservoir pressure, I have to change it, and I have to use this number here, right? Unlock it. Yes, and I have to use this number here also. Okay. Then I want to plot that, just so you have it. Yeah, I'm just going, I change it, and you can also change it, but also to keep it in the notes, okay? So that will be IPR for PR equal to 250 bar, and the rates will be here, and the pressure will be here. Okay? Actually, they are not completely parallel. There are some, you see, they're open, they are smaller here and more wider here. Okay, but that's the effect. Let's use another color. I don't like this green. Is it difficult to see? And there are some people that they have problems with some colors, and this might be one of them. And I'm going to put also the legend so I know exactly what is what. Okay, to get the legend, you click here on this plus, and then you check and click on the legend. Okay, and then you can drag it and move it any place in the plot. So for the exercise you're going to make, please use this format so it looks nice. Line fill, solid fill, and then here. Okay, with depletion, the equilibrium point moves to the left, which makes sense. Okay, every time, each time the well can produce less and less. Okay, now I ask you once more, what happens? There is a, let's say there is a new engineer, okay, that came to the company and says, I have an excellent idea. If we change the tubing size, okay, we do a workover on the well, it's a big job, okay, have to pull out all the tubing and then put a new one. That will increase dramatically the production of this well, trust me. Okay, so how can we evaluate that? What will we expect will be the effect of changing the tubing size? Okay, okay, so let's see changing tubing size, okay, and that means changing the diameter, the ID, the diameter of the tube. Okay, again, let's take out the previous plot we had, original plot. Okay. What will be the effect? What is changing the ID makes to this plot? What do you think? Is it changing the blue curve or is it changing the red curve? The red one, okay, because the red one is the TPR. That's the tubing. Actually, that's okay. So if I say intuitively, if I use a bigger diameter, okay, what should happen to this curve? Should I have more pressure drop or less pressure drop? If I make the pipe bigger, if I make the pipe bigger, okay, the velocity goes down, okay, and then I have less pressure drop. Okay, so how it looks like in this drawing, should I try to make an attempt how it will look like? This point will be exactly the same, yes, but then I move and maybe it might be something like that. Okay, this is for tubing with bigger diameter. Okay, we are now talking intuitively. What happens if we increase the diameter? And if we decrease the diameter, make more pressure drop, what should happen? The curve, how does it look like? Okay, something like this, right? I have more pressure drop and that makes sense. Now the equilibrium point, the rate that I can produce is less. This was the original and here is more. Okay? Tubing with smaller diameter. Yes, intuitively. You think that that's what will happen. But now, looking at this plot, really, let's assess a bit what this engineer said, okay? This engineer said, this well looks very bad. I can go and change the tubing and you will get much, much, much more, okay? So you come here and assess, okay? You say, it should, if I use a bigger size tubing, I should have a curve like the brown one, okay? Or something less. What is the minimum really if I make it an extremely huge tubing? What will be the minimum that I get? Something very close to this value, right? Almost no pressure drop. It will be almost constant. It will be very, very, very small, right? Yeah, that's correct. So that means the maximum flow that I'm going to get using let's say this is a huge tubing, okay, something it's incredibly large, such that I almost have no pressure drop, I will get a gain in production from the original rate that was, if you remember, this number was 2.85. You just calculate it now. And now I will have something around 3. Okay? How much is that in percent difference in percent? You know how to calculate relative difference, right? The relative difference is the original rate, QG original, minus the new rate, QG new, that I could obtain divided by QG original times 100. Yes? Or, well, actually the opposite, because we have, we are increasing the rate. So we are going to say how much more in percentage we're going to get from this well. If we do what this engineer came and he said he's the wisest man in the world. Okay, so how much is that? This is 3, this is 2.85, and this is 2.85. So anyone can make that calculation for me? Huh? 5%. Okay, increasing the rate of the well. Okay, what are you going to say, this engineer? Okay, if it's a gas well, maybe, I don't think it's worth all the trouble. Okay, intervention might be an extremely, if it's onshore, for example, it might be in the order of maybe 1 million, half a million dollar to change the tubing. And really you have to say, okay, that increase has to be significant such that it pays for that intervention without doing any calculation. Okay, so far we didn't put any number. We just look at the plot. Okay, look how the curves look like, and see what will be the maximum if we use a very large tubing, no pressure drop, the maximum pressure that we can get, or the minimum pressure that we can get. Okay, just from observation. And that's why I tell you this curve is extremely important, that you have to understand what it means and how do you change each one of them. Okay, that clear? Yes, a small tubing, what happens, and if you use a very, so that means, okay, if we say this, our well is not tubing restricted, okay? That means your well really, the tubing size is appropriate, is a good size for that well, okay? Because it's not creating any restriction, any good restriction on that well. Okay, if I'm going to invest my money of that well, maybe I will do something on the IPR. Okay, maybe I will fracture, I will perforate, I will do something such that this curve, instead of looking like that, it will look something like this. Okay, it will increase the productivity. But for my opinion, it doesn't look like I want to invest money changing the tubing on that well. Okay, and that's why I call it's not tubing restricted. Okay. Now, let's look at the equation, at the tubing equation. Okay, so we said it's P2 squared minus P1 over e to the s minus QG squared over CT squared. And remember that CT, we did it last class, was pi over 4 R over molecular weight of air, 0.5 PSC over PSC. You already memorized the equation or not yet? Not yet? Well, that's not so important. Okay? So that's what C looks like. And let's see, so what is the effect of increasing the diameter? What does it do to the C? Okay? So look at that expression and see where the diameter is. Actually, it's exactly proportional. Okay? It's 2 to the 0.5. So that means if I increase the diameter, an increase in diameter will lead to an increase in C, okay, in CT. Yes, so that's how we can more or less, that's how we can assess like changing on the IPR, okay, like we change on the IPR, we change reservoir pressure. If this curve, if we want to assess the effect of the tubing, we can increase or decrease the CT, okay? So by increasing the CT, we can assess what will be the effect of a bigger or smaller diameter, okay? And actually, if we say we can actually use this equation, if only the diameter changes, if only the diameter changes, then we can make this expression, okay? We have CT1, that is a function of diameter 1, yes? And then we have CT2, that is a function of diameter 2, okay? And what happens if we divide these two expressions, CT1 divided by CT2? All the rest is going to be constant, okay? All the rest, nothing is going to change. Only this diameter for 1 and this diameter for 2. So CT1 divided by CT2 is going to be equal to Phi1 to the 5 divided by Phi2 to the 5 to the 0.5. Okay, that means Phi1 to the 2.5 over Phi2 to the 2.5. Okay, so if we have, for our current diameter, if we have the diameter, okay, we can calculate what would be the C if I use another diameter. Okay, so I say, for example, CT2 will be equal to CT1 times over Phi1 to the 2.5, Phi2 to the 2.5. Okay, so this one I have, and this one let's say I have, so I can calculate the new CT without calculating all the rest. That clear? Yep. Okay, so let's do a test. So that plot I'm going just to take away to avoid confusion. That was the effect of depletion. Now let's see what will be the effect of changing the CT. If you go to the Excel sheet, you see here at the bottom you have tubing constants, and these are the numbers that we are using. Well, it's very similar: 164.2, 164.2. Okay, these two numbers for C and T. But now let's see what happens if I use a much bigger tubing. Let's say 0.18. Okay, 8. Some time, 8. Okay. You see that the elevation coefficient remained the same, but CT now instead of 4.2 now is 5.8. Okay, so let's put that in our Excel sheet. It was 580. Okay, and you see the curve went down, not much. So the gain really by changing it is not much. Let's make it smaller. Let's see now if it's this was like 7-inch. Okay, so 2-inch is how much? It's 54. Okay, 0.54. That's 2-inch. So 2.51. 2510. Something happened here. Okay, now you see the intersection is actually here. It is restricted very, very much the rate of the weld. From going from 2.8, it went all the way to 5. Okay, like 6 times reduction in the rate. Yes. Okay, now here I want to make some comments, okay, on that. So keep that in mind. So let's Um, let's see, what did I do here? Okay, we're not going to make it here, but you can make the plot. There are so how tubing sizing? Okay, how do I determine the best size of the tubing? Okay, and there are different factors. One of them is just the casing. Okay, the size of the casing. You cannot use a bigger tubing than the casing that you have. Okay, so it comes determined by the ID of the production casing. Okay? Another thing is the size of the hanger. Okay, I told you that you have the tubing is in one structure that looks like that. Okay, that's the tubing hanger, and sometimes you have to pass, I told you, other things through the hanger. Okay, like you have the hydraulic line, you have the power of the, if you have a pump, or if you have the pressure gauge. So that hanger, if you see it from the top, okay, looks something like that. It's like a disc, and we will see if we have time to see, but we have a disc, and there we have the hole of the tubing. Okay, so that's the tubing, and we have the other holes for all the different things. Okay, that might be the power cable, that might be the pressure transducer, that might be the hydraulic line. Okay, and if you make that tubing extremely big in that hanger, then first you have no space for everything else, and also you it's like if you have less and less material, then it doesn't have enough to be for its strength to be structurally strong. Okay, so that's why we're limited because of the tubing hanger. So the size and amount of holes on the tubing hanger. Okay, maybe the casing is very big. Okay, but maybe in the hanger I have to pass a lot of things inside, so I don't have much space available. That's especially true for subsequents. Sometimes we have also scale injection. We have, a scale inhibitor. We have other things to inject. We have the emulsifier that we want to pass by, and then we have a lot of pipes, and it becomes smaller and smaller and smaller, the type of tubing that I can have. Okay, and of course, one more thing. So that's on the the physical part. One thing is that to reduce the pressure drop in the tubing and increase production. Okay, we want to use a tubing PWF versus Q. We want to use a tubing that actually doesn't restrict very much. I don't want to use a tubing that looks like this, but actually I want to use number 1 is better than number 2. Okay? Just because I get more production, the pressure drop through the tubing is less. But there are two more aspects that we have to consider. Okay, one of them is erosion. Okay, if we use a very high speed, then we will have erosion, and we will start to eat up the wall of the tubing. Okay, we will have to create erosion inside the tube. So the velocity of the gas has to be less or equal than a certain erosional velocity. Okay. And this is defined usually by the API 14E. Okay, and that equation says that the erosional velocity, and that equation came erosional. If you go above that velocity, the gas or the liquid or the fluid, the mixture flows more than that, more than this erosional limit, then you will have problems. And that's equal to a C, a constant, that constant is between 100 and 120, okay? And the square root of the density of the mixture. That was found on laboratory. It's completely empirical. Doesn't have, but if you use, for example, you use oil or you use a more kind of dense fluid, then you will have more erosion. Okay, because this becomes smaller. Sorry, if you use gas, this becomes smaller, and then this velocity becomes higher. Okay, that means you need to have, for gas, you need to have a much higher velocity to have erosion. Okay, while for liquid, the velocity can be much smaller. Okay, that's the limit. Okay, cannot go above that. And here that equation, this is for units, this is in feet per second. Okay, and that density is in pound mass per cubic feet. Okay. Now I ask you, how, if we have that velocity, how, where do we have to compare it? Okay, in the tubing. The tubing, remember, if I see along the tubing, I put an X along the tubing. I ask you, is the velocity of the gas, how is it going to be? Constant or changing along the tube? Huh? Changing, okay? Because I told you that, remember, the velocity of the gas is the rate of the gas, local, at P and T, divided by the cross-section area, okay? And this Q is the Q at standard conditions times the Bg at that pressure and temperature, okay? Divided by the area. And remember what was the behavior of that Bg? We did it yesterday with pressure, goes like that, okay? So Bg, let me put that in a new sheet. Okay, and it goes something like this. Okay, that means that the velocity of the gas is going to be higher where? At the wellhead or at the bottom hole? Where is the pressure higher? In the well. So here we have P wellhead and here we have P bottom hole. Okay, this one is bigger than this one. Okay, that means the velocity, if this one Bg is small, then the velocity is going to be also small. Okay, but it's going to increase as I decrease the pressure. You see that? Yeah. So if we plot along the tubing, let me just make it here. I will try to make it, okay, X, and I plot the pressure first. Okay, the pressure is going to go actually down, okay, from these two values. But if I plot now the velocity of the gas, okay, how is it going to go? The opposite way. Okay, it's going to go from a very small value to a very high value. So I ask you, if you want to check if you're going to have erosion or not in this well, what will you use? Okay, you are going to check the most critical point, which is the wellhead. Okay, that's the highest. And if I violate here, if at the wellhead, the velocity of the gas is greater than the erosional velocity, that means that I have a problem. Okay, I have a problem. I might have erosion in the tubing. Okay, if Bg is less or equal than the erosional velocity, what does it, could I have erosion any other place in the tubing? Yes or no? Well, not really, because that's the maximum velocity I'm going to get in the tubing. Okay, that's the maximum. And if I don't have any problems there at the wellhead, that means that I don't have any problems any other place. Okay, that clear? Okay, so yeah, I calculate with this API, I calculate the maximum erosional velocity. For that, I need to have the density. Okay, that means that is going to change also with pressure. Okay, but I compare also in the most critical part of the well, which is the wellhead. Okay? If I have a problem there, I might have erosion in the tubing. I have to check. If not, then usually I'm safe because that's the highest velocity that I can have in my whole system. Okay, that clear? So let's go through it. So production sizing, we want to reduce the delta P in the tubing. We want to fit the casing. We want that it will have no problem with the tubing hanger. We want to have erosion. And there is one other detail that we have to keep. So the gas, if I'm producing with associated liquid, if producing with liquid, okay, then the gas has to be able to lift the liquid out of the well, okay. Otherwise, if I don't do it, okay, if for some reason there is some liquid, and we will see later what are the sources of liquid in gas wells, okay. But if for some reason, let's say this is gas and it's just flowing up, and also I have some liquid coming in, okay. So that's the Q of gas, but I also have some liquid, and this liquid, it might be condensate, it might be water, okay, something like that. So I have to QG has to be high enough such that it can carry the liquid, okay, the Q of the liquid. Otherwise, what's going to happen? I'm not sure if you saw that already, some other course, but what will happen is that the liquid will start to accumulate with time, okay, accumulate and accumulate and accumulate, and at the end it's going to create like a plug that is going to impede for the well to keep producing, okay. So that's what is called liquid accumulation in the well bore, and that's what is called liquid loading, okay. Very important for gas wells, extremely important. I want all the liquid to be carried with the gas. When the gas doesn't have enough energy, enough velocity to pull it up, then the liquid is going to accumulate, and then you will have a back pressure against the well, and the well might die, stop producing very early, because this height with this density of liquid creates a huge back pressure against the well, okay, and then kills the well. So how, okay, so now we know we have to have certain critical velocity to lift these droplets of liquid. So how we come, how we determine that velocity? So if we make a force balance on a droplet, okay? We have a droplet of liquid and we have gas blowing up, okay, this is the gas and that is the liquid. Okay? And in that configuration, we have basically two forces. We have one which is, if you have some flow or some fluid flowing through in front of you, you have something that is called the drag, okay? You have a drag force that is pulling it up. So that's the drag, okay? And then you have some other force that is the force that is going down. That is just because of the weight, okay? But remember, this droplet, if you have a droplet, okay, suspended in a medium, okay, the effective force going down is actually the weight minus the buoyancy, okay, because you have that when it's submerged, you have also the buoyancy that is trying to pull it up, okay. So let's write those two forces, and if I say in the critical point the critical velocity is such that these two are equal, in reality I want that the drag will be always greater than the weight, okay. So let me put here phi and F buoyancy. So I say F drag should be equal to F of the weight. Okay. And then So what expression do we have for the weight? It's the density of the heavier phase minus the density of the gas, okay, multiplied times G multiplied times the volume of the droplet, right? What is the volume of the droplet if we assume it's spherical? If you remember, I think it's something like pi phi to the 3 divided by 6. Is it? I think so. I'm going to check. Okay. And then I have the drag force that you know is 1 over 2 of a coefficient called CD. Okay, the drag coefficient times the density of the fluid, density of the gas, times the velocity of the gas squared. Yes? The drag force. Let me just check if I'm not making any mistake. And of course, the projected area AD, the projected area of the sphere. Okay, if the gas is flowing in that direction, it will see just a circle. Okay, and this AD is pi phi squared over 4. Okay, so now I can put that together. So let's see how I end up with V equal to square root of phi g rho L minus rho g for third of CD over rho g. Okay, so I have two big unknowns. This one I know I can calculate at any point in the tubing, okay, with the real equation of state. This one I can get from PV, Z, and RT, okay. The rho of the liquid the same way. I say, well, the liquid really doesn't change much. It will have a change with density, but let's say not much, okay. So I can also say this is relatively constant. Okay? At the gravitational acceleration, but now I have two things that I don't know: the diameter of the particle, okay, and this drag coefficient. This drag coefficient, if I'm saying, remember the gas is always turbulent, so it's always in the turbulent region. So this means that this C in the turbulent region is 0.44. Okay, because if you remember the CD versus the Reynolds number, that actually does something like this and is stabilized, okay, at 0.44. Now comes the diameter. So there was a researcher, actually he worked with Shell in the Netherlands, called Hinze, okay, and he did experiments. He said, I want to find exactly how I determine for a certain flow what will be the diameter of the droplet. Okay, and I can have really in a well, I can have many. If you imagine the cross section of a well, okay, and gas flowing, you can have many droplets of different sizes, big, small, etc. Okay, but he said, I don't care about all droplets. I don't want to predict exactly every droplet size that I have, but I want to predict the D maximum. Okay, and that's exactly what we need. If we do the balance and we do it for the bigger droplet, then we know it's going to be satisfied for even the small ones. Okay, so I want exactly what this Hinze did. So he said, he was very smart. So he said, I define a number that I call the Weber number. Okay, and that Weber number is defined by density of the gas over D, and that's phi. That's actually the diameter of the droplet divided by the interfacial tension, okay, between the two phases. And if you see, it's like two forces, okay. Every adimensional number is like a force, like Reynolds number. So here initially we have some inertial force, okay. Velocity squared is like kinematic, is some inertial force that is trying to tear the droplet apart. Okay, it's something that is trying to make it smaller, smaller, and smaller. And here we have the interfacial tension that actually is an interfacial force that is trying to keep the droplet together. Okay, so you have the fight between these two things. So he said, his main observation said, when this Weber number, NW, is equal to 30, that gives you the max. Okay? By observation, run many experiments. He said, you know, exactly when I have 30, that gives you the maximum droplet number that I'm going to have. And voila, I have the equation, the other equation I need. Okay? The other equation I need is this UG squared, density of the gas, phi max, divided by sigma equal to 30. Then I substitute this equation in 1, okay, in this equation that I had here. And then I solve my two problems that I had, the CD and the diameter. Okay, and at the end I end up with this equation that is the famous, I guess you have heard the name, Turner equation. Okay, that is V is equal to 5.46 sigma to the 0.25 rho L minus rho G, 0.25 divided by rho G to the power 0.5. Okay, with density in kilogram per cubic meter and sigma in Newton per meter. Okay, and that's all. That's it. So I'm making all of this development. There was one more condition. Remember, erosion, tubing size, pressure drop, but there is also one more. If I have liquid, I have to be above this velocity to be sure that I am able to take it out of the well. Okay, so that means if I go on, then an engineer comes, I'm very smart. Okay, I'm going to make the tubing very, very big. I have a very low pressure drop. When I make it, I have a very low gas speed. Okay, and then it won't be able to carry these droplets, and then my well is going to die anyhow because I didn't take into account that the gas has to carry the liquid. Okay, so that's the third condition that I need here is erosion. Okay, idea of the production casing, size and amounts of the tubing hanger. I want to reduce the delta P. I want to avoid erosion. Okay, I don't want to use a very small tubing, but I also want to avoid liquid loading. Okay, and that means that the velocity of the gas should be always greater than the Turner velocity. Okay, that is the expression that I calculated before. Many conditions, okay, that I have to fulfill, and I have to check all of them. You cannot overlook. All of them are going to kill your well. Okay, this one you cannot. This one is going to affect the structural of the tubing hanger. This one will reduce dramatically. This one really is going to kill very quickly the tubing. It's going to make holes in the tubing. I don't think I have a picture of erosion here, but it's going to, kill it very quickly, remove the material very quickly, and avoid liquid loading. That also kills gas wells very quickly. Okay, all of these considerations. And if we have time, we're going to make a small exercise on that when we look at how we calculate the pressure along the tube. Okay, now we are calculating only at the inlet or at the outlet. But we are going to look maybe tomorrow what happens if we want to calculate in between. Okay? That clear? Yes? Okay. Uh, okay, now I have one more question for you. So that's how to define the size of the tubing. So we saw, okay, just to summarize, we are covering many things today. We have depletion, okay, reduce the IPR. We have the tubing size is changing this curve up and down. And we have what is the effect of the wellhead pressure? Okay, QG and PWF. I have these two curves, okay? So this is the effect of depletion. Okay, well, basically it's not like that, making a, and you are also sleepy, like that, right? Depletion goes down. The tubing size, this is the tubing size, okay? And what is the effect of the wellhead pressure? If I change the wellhead pressure, for some reason I can, put a separator that operates at not at 40 bar, but at 30 bar, at a lower pressure. What do you think is going to change, changing the separator pressure? First, let's, narrow it down. Should it affect the available or the required, the IPR or the TPR? Okay, the TPR. Okay, IPR doesn't, I don't see here, I don't have separator pressure at all. Okay, I just have it here. So how is it going to, now we know it changes this curve. Okay, intuitively, what happens if we reduce the pressure from 40 to 30? Should we get more rate or less rate? More rate. Okay, so that means that the intersection should be shift to here. Okay, now I ask you, when it's no rate 0, should the point be the same or should it be lower? Also lower, okay? Because that pressure is less. I have the same hydrostatic column, and then that pressure should be also less. So actually, what the changing the which color do I use? Changing the wellhead pressure makes this effect, okay? So this is changing PWH, okay? If I reduce it, I will have more rate, and if I increase it, I will have less rate. Okay, but actually it's like shifting. Okay, one of them, the tubing size, is just scaling it, but it's keeping the same endpoint, but the other one is shifting it up and down, the separator pressure. Okay, so let's, we have again our Excel sheet. It's very nice. We can just did it properly, so we can assess here what will be the impact. So let me go back to the other 5.8, and it was 4.25. Okay, that was for our original case. So I'm going to increase it now. Instead of 40, I'm going to use, let's say, 60. Okay, separator pressure. Did you see it shift up? Now let's use, for example, 100. Okay, you see it shift up, 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 reaching the equilibrium. Or if I put now 20, for example, okay, it also changes the equilibrium. Um, Now, saying that um, reducing or changing separator pressure is not something that we normally do. Okay, because changing is like you have to change the control, you have to change many things in the downstream process. So usually we want to keep it constant. So a way to change it, to change reservoir wellhead pressure, is to put a compressor, something that sucks, okay, the gas out of the well. And then with that, you can reduce it almost all the way to atmospheric. If you put a compressor, you have your well, okay, and then here you connect a compressor that is sucking from the well to the separator, okay, and then you are able to lower the wellhead pressure almost all the way to atmospheric or even vacuum. Okay? And that's how we achieve this effect. Okay, clear? Yes. Now we have, I think like maybe 10 minutes or 15 minutes, and I want to do something else. Now I want to change the point, and I want to move it from the bottom hole and do the equilibrium at the wellhead. And I want also you to try it with me with the same Excel sheet we have and perform wellhead equilibrium. Okay? Okay, that means that I already have the IPR. Okay, if you remember our system, I had a choke that was open. Okay, remember that choke was not working. Open. Okay, and initially we selected our point here. Okay, but I told you you can do any place you want. So we want to calculate now making it here at the wellhead. We want to make the equilibrium point there. So I ask you, what else do we have to make? Remember, we have to move, okay? We want to calculate the available from here to here. That we already have, right? And then we want to move from here to here. And that's the part that we are missing, okay? So how do we do that? How do you suggest? What do you suggest? Well, I suggest we already have this point, right? We have this PWF and we have this rate. So why the only thing that we need is to use the tubing equation to calculate this pressure. Okay, remember the tubing equation is using two pressures, P1 and P2. In the previous case, we have used tubing P1, right, to calculate counter current from here to here. But now we have P1. We calculated from here to here. And now we have to compute P2. Okay? So let's make a change, okay, here in our Excel sheet. Okay, I'm going to move that part away. IPR. Okay, and I'm going to create one here that is going to be WPR. Okay. That means wellhead performance relationship. Okay. I'm moving the equilibrium point at the wellhead, and that will be P wellhead, and that will be P wellhead actually available. Okay, in bar. And here let's do it very extremely careful. Here we know we have to use the tubing equation, and we want to calculate P2. Okay, we have P1, we have the rate, and we want to calculate P2. So I say tubing tubing P2. Okay, want to calculate the pressure at the discharge of the tubing using CT. I block it. Using the elevation coefficient, I also block it. Using the pressure at the inlet of the tubing, which one is it? This one, right? Okay. And the rate here, okay, 281. If I have no flow, I have bottom hole is reservoir pressure, I will have 281 at the top, okay, and then I drag it down. And here you see we got some strange problem, but let's see. So let's see, how do you expect that curve to be versus rate? Like that or like that? Is the available pressure, okay? So it should look like that, okay, going down. So let's plot it here. Select data, and then we say WPR, okay? And that will be with reservoir pressure equal to 304 bar. And I'm going to select the rate, and I'm going to select the pressure. Okay, and I don't want to plot any negative pressure, so I want to change it here to 0. Okay, and this green curve is my WPR. Okay, exactly the shape that we were expecting, but smaller than the IPR. What is the difference between these two? Okay, now I ask you, that was the original equilibrium, okay, these two curves, and I'm making it on purpose, just, to be sure that you're sharp. These two are for bottom hole equilibrium, okay, these two. Now I calculated the green one, and this is the WPR. That means that this includes the IPR and also the tubing, the TPR, both. It includes both. But the difference between these two is just the pressure drop, delta P, in the tubing. Okay? Just like that. Because you have a pressure at the downhole, and then when I move to the surface, just because of the flow through the tubing, I have less pressure available. Just like that. Okay? Clear so far? Yeah. Just bear with me. We still have some minutes to go. So how do I find now the equilibrium rate? Remember, it should be the same. If I put the point at the wellhead, I put the point at the bottom hole, should give me the same. The analysis should be consistent, should give me the same point. So what do I have to intersect this curve with? This WPR. What is if I look at my diagram? Okay, I have separator. Okay, that's constant. Then I move back. This is a very short piece of pipe, so basically that pressure is always equal to that pressure. And the choke is fully open, so that pressure is actually equal to that pressure. It has to be equal to a constant separator pressure. Yes? Okay, so I come here and I say, what is the pressure? 40 bar, right? Let's use this green. 40 bar, and that should be constant, and that's where the intersection should be. Okay, and that point, that rate here, should be equal to the rate that I find with the other equilibrium. Okay, the two of them should be exactly the same. Yes, different point, different place of analysis, different curves, but the equilibrium should be the same. Correct? Now to finish, okay, you're tired, you want to go, you want to put some to rest the brain. Now we can do it. Okay, what if I want to produce okay, I calculate now, because of erosion on the tubing, I cannot produce more than 1.5 million from this well. Okay, came the engineer, said, this well is very nice, can produce a lot, but for the tubing that you are using, you cannot produce more than 1.5. You're limited to 1.5. You say, what to do? I have to start using the choke, right? And what delta P I have to put in this choke? So I just come here, okay, and I say, well, for 1.5, the available pressure that I have is close to 205 bar, okay? But the required pressure is constant and actually is 40. So I have to put a choke that will bridge these two pressures in one reduced and concentrated space. I have to bridge these two pressures. So I have to put a choke that will give me this delta P. It means the delta P of the choke has to be equal to 25 minus 40 bar, and that gives you how much is that? 265? Sorry, 165 bar delta P. Okay? And then I go to my operator, I can do it myself, I go to the field and I start closing the choke until I get exactly 164 bar pressure difference. That clear? Yes? Okay, now your homework, okay? So that will be number 3. Okay, you're getting, I told you, you have to do them on time because otherwise you will be filled with homework. So the homework is to perform flow equilibrium, for this class exercise, but using the wellhead has the equilibrium point. That means do exactly what I have done just now. Calculate the available pressure at the wellhead, okay, and then find separator pressure, and then you make the difference between them, and then you drive to zero using the solver, okay? So that means compute WPR, okay? Then you say WPR minus P separator, okay? And then you say find QG such as WPR minus P separator is equal to zero, okay? And make the plot. And the last part of that exercise is find delta P of the choke such as the Q of the well is equal to 2 million standard cubic meter per day. Okay, just what we have done just now. Actually I solved the homework for you. So you have to say I'm in a good mood, I'm nice, and I'm solving the homework for you. Okay? Yes. So let's summarize. We did. You're using Excel. You learn to plot. You learn to use macro. You learn to use the solver. We made one example making IPR and TPR intersection at the bottom of the well. Then we say, okay, what is the effect of changing the tubing diameter? What is the effect of the depletion? And what is the effect of changing the wellhead pressure? These three effects. Then I told you how we select the tubing size is not so simple. There are like a ton of things that we have to take into account that are casing size, tubing hanger size, erosional velocity, I want to reduce the pressure drop, and I want to liquid loading. Okay, these five things that you have to take into account when you design a tube. And then we made the equilibrium at the wellhead, okay, and that's the homework you have for by the end of the course. Okay, any question before we close? No questions? Okay, we finish. See you tomorrow.